Now let me move on to discuss about parallel combination of capacitor. What is meant by parallel combination? See, if two or more capacitors are connected across their common points, common ends. Okay, that means if one terminal of all the capacitors are connected to one point and other terminals of all the capacitors are connected to the other common point, then we call that as a parallel combination. That means this is the first end and this is the first end. All these first ends are connected together and all these second ends are connected together. That is called as parallel combination. That means parallel combination means if one end of all the capacitors are connected together and other end of all the capacitors are connected together, so that the potential across each capacitor is same, which is same as that of the potential of equivalent capacitor, but not the charge, is called as a parallel combination. That means charge is not same for individual capacitors in the combination, but potential difference across each and every capacitor is same in the parallel combination. Okay, so parallel combination of capacitors is that the potential across each and every capacitor is same but not the charge present in the individual capacitor. That means the one end of all the capacitors are connected together and other end of all the capacitors are connected to the next end. That is called as the parallel combination. Okay. Now we have to discuss about what is the capacitance of the equivalent capacitor in parallel. Consider two capacitors. So that is having capacitance C1 and the capacitance of second capacitor is C2. And charge in the capacitor C1 is Q1 and charge in the capacitor C2 is Q2. Since these two are connected parallelly, the potential difference across each capacitor is same according to the definition. And the equivalent capacitor is having the capacitance Cp and potential across that is V. And let us take charge of equivalent capacitor is Q. The charge present in the equivalent capacitor is always equal to algebraic sum of the charges present in the individual capacitors. Okay, so Q can be written as Q1 plus Q2. We all know capacitance is the ratio of charge to potential difference. So Q is equal to C into V. In parallel combination, potential is same. Potential difference is same. Right. Now substitute this value. So here we can write for the first capacitor, the charge present is Q1 is equal to, according to this expression we write, capacitance of the first capacitor is C1 and potential across the first capacitor is V. And for the second capacitor, Q2 is equal to, capacitance is C2 and potential is V. And for the equivalent capacitor, so charge is Q and capacitance is Cp and potential is V. Now substitute all these values in this equation. So Q is nothing but Cpv, that is equal to Q1 is C1v plus Q2 is C2v. Now take V as common. So Cpv is equal to, if we take V as common, we write C1 plus C2. This V and V gets cancelled. Therefore, capacitance of equivalent capacitor in parallel combination is equal to algebraic sum of the capacitance of the individual capacitors. Suppose if we connect n number of capacitors in parallel, if we connect n number of capacitors in parallel like this, then the capacitance is given by Cp is equal to C1 plus C2 plus C3 up to n capacitor, that is Cn. And if all those n capacitors are identical means all the capacitance are same, C1, C2, C3 are all same, let it be equal to C. Then we write the equivalent capacitance as Cp is equal to, in place of C1, C, in place of C2, C, in place of C3, C, up to N we have to add. So we are adding N times C, so Cp can be written as Nc. Okay. So this is the expression for the equivalent capacitance when two capacitors are connected in parallel. When n capacitors are connected in parallel, then it is C1 plus C2 plus C3 up to Cn. If all those n capacitors are identical, then their equivalent capacitance is Cp is equal to n times C. This is about the parallel combination. Now let me move on to discuss about the energy stored in a capacitor. Let us consider the two conductors, so conductor 1 and conductor 2. Here, in order to transfer the positive charges from this conductor 2 to conductor 1, we need to do some work against the direction of electric field. So, suppose initially if these two are uncharged, they are in neutral condition, the charge on each conductor is 0. After some time, we are doing some work and moving some charges from conductor 2 to conductor 1. Let us take the charge on each plate is, each conductor is Q at the intermediate situation. Finally, we are moving all the positive charges from conductor 2 to conductor 1. So, charge on the final charge present on both the conductors is Q. Let us take the intermediate situation. At the intermediate situation, the potential difference between the two conductors say as V dash. Okay. So, we can write the charge at the intermediate situation as Q. In order to calculate the capacitance, energy, let us consider, what is the amount of work done, smaller amount of work done to move the smaller amount of charge dq from conductor 2 to conductor 1. Okay. So for that, let us consider, we know from the definition of potential difference is nothing but the amount of work done to move the charge from one point to other. That means from one conductor to other. Right. Here the potential difference is V dash. Therefore V dash, let us take dq here, into dq is equal to dw. So the smaller amount of work done is nothing but dw is equal to V dash into dq. Okay. So then the total amount of work done to move the charge from 0 to q is given by integral of. So we are adding all the smaller amount of work done from 0 to q. Okay, we are moving the charge initially from 0 to q. At the intermediate situation, it is capital Q. Okay. Now W is equal to, we write integral of dW means it is nothing but V dash into dq from 0 to q. Here, from the definition of capacitance, we write C is equal to, we can write C is equal to Q by V. At the intermediate situation, the charge is Q and the potential is V dash. Right. So, V dash can be written as, now cross multiply. V dash goes here and C comes to the denominator. Therefore, Q by C. V dash can be written as Q by C. Now substitute here. So we write W is equal to integral of Q by C into dq from 0 to small q. Now this 1 by C is constant. Capacitance for a capacitor is constant. So W can be written as, now take 1 by C outside the integral from 0 to q, q dq. Now see, this is in the form of the integral of x power n dx, that is equal to x power n plus 1 divided by n plus 1. Right. So we can write W is equal to 1 by C into, after integrating this q dq, we get q. Here power value is 1. So 1 n value is 1. So in place of n we can put 1. 1 plus 1 divided by 1 plus 1 from 0 to small q. So W is equal to 1 by C into this can be written as Q square by 2 from 0 to Q. Right, this is the amount of work done. Now I will write here. So therefore total work done is equal to 1 by C. First apply the upper limit, so Q square divided by 2 minus next apply the lower limit 0 by 2. 0 by anything is 0. Therefore, amount of work done is, we write 1 by 2 into Q square by C. This amount of work done will be stored as a potential energy. The amount of work done in transferring the charge from second conductor to the first conductor will be stored as an electrostatic potential energy. Therefore, we can write, what we can write? So, amount of work done is nothing but the potential energy. Therefore, U is equal to half Q square by C. This is the expression for energy that is stored in a capacitor. Okay, energy stored in a capacitor is given by 1 by 2 Q square by C. The other forms of this expression can be written as, we know Q is equal to CV, right, product of capacitance and potential. Therefore, this can be written as half in place of Q square. So, we write Q square means CV whole square, that means C square V square divided by C. This C and C gets cancelled. So, the potential energy can also be written as half CV square. U is equal to half CV square. And we can also write in place of C Q by V. So, we write U is equal to 1 by 2. In place of C, capacitance is nothing but ratio of charge to potential. So, in place of C, we can write Q by V into V square. This V and V gets cancelled. So, potential energy is equal to half Q. Now, the other forms of the expression for potential energy or energy stored in a capacitor is half Q square by C, half CV square and half QV. These are the expressions for energy stored in a capacitor. Now let me move on to discuss about energy density of a capacitor. What is the energy density of a capacitor? Energy density means mass density means mass by volume. Energy density means in a similar way we can say energy density of a capacitor is defined as the energy stored in a capacitor per unit volume of that capacitor. Okay, so energy density of a capacitor can be defined as the energy, electrostatic energy stored in a capacitor to or per unit volume of that capacitor. And the SI unit of this energy density is, unit of energy is joule, unit of volume is meter cube. So, joule per meter cube. Now, what is the amount of energy density of a capacitor? Let me move on to discuss about. The energy stored in a capacitor as half Q square by 2C. We have derived that expression. So, from previous derivation, the energy stored in a capacitor is half Q square by 2C. And we all know the surface charge density is the ratio of charge to the area of the each plate of the capacitor. So, Q can be written as sigma into E. In the case of a capacitor, we know the electric field between the two plates of a capacitor as E is equal to sigma by epsilon naught, that we have derived. Okay, so in previous classes. So we can write sigma as, now take this epsilon naught here, sigma as epsilon naught into E. Now substitute this in this equation. So we get Q is equal to sigma means epsilon naught into E, that into E. Okay. So we get the value of charge present in a capacitor as epsilon naught EA, where E is the electric field between the two conductors of the capacitor and A is the area of each conductor. Epsilon naught is the permittivity of free space. Okay. Now substitute this in this equation. So we get U is equal to half Q square means epsilon naught EA whole square divided by, see, this is half Q square by C. Okay, expression for energy stored is half Q square by C, sorry. So divided by C. So capacitance of the parallel plate capacitor or capacitance of a capacitor. So when air is filled between the two conductors of the capacitor is given, that we have derived in the last class, as C is equal to A into epsilon naught by D. Right? This we have derived in the last class. So now substitute this C value here. So we write U is equal to half into, now by squaring we get epsilon naught square E square A square divided by C means A into epsilon naught by D. Right. This A and 1A, epsilon naught and 1 epsilon naught gets cancelled. Now take D to numerator. So we can write U is equal to half into, remaining is epsilon naught E square 1A, and this D goes to numerator D. Right. So we can write U is equal to, this area into distance is called as a volume. Area into distance will be called as volume. Now take this to this side. So U by A into D, that is equal to, remaining is half epsilon naught E square. Okay. So this is nothing but the energy stored in a capacitor and this is the volume of the capacitor. So energy per unit volume is nothing but the energy density. Okay, energy density, and that energy density is equal to half epsilon naught E square. This is the expression for energy density of a capacitor. Okay.